So today we are starting with a look at electricity. Now this here that I have with me today in the classroom is a circuit board, which is a way for you to play with and experiment with and do some investigations with direct current electricity. Okay, it produces direct current and electrical current obviously. And what we are using here is we've got some batteries that are our power source, which are all lined up there. So there are our batteries, which are going to be our power source. Then we have some apparatus to measure the different aspects of electricity. So the one on the right of the screen is called an ammeter, and that measures how much electrical current there is flowing. So remember, the way that you can think of current is like water flowing down a river. So if we had to measure the amount of current in a river, we would be measuring the rate of flow of water flowing down the river. This measures the rate of flow of electrical charge, and it's called an ammeter. That's why it's got a capital A on the gauge there. And the other one is called a voltmeter, and that measures potential difference. Now you can think of that as the gradient down which the river is flowing, so that the difference in gradient when you're talking about a river is what enables the current to flow, and using that same analogy, the degree of potential difference, or how much potential difference you have, is what enables electrical current to flow. So we have an ammeter and a voltmeter. A voltmeter must be connected in parallel. So you'll see the way that we connect it up so that it gives us an accurate reading, that we connect that meter in parallel, whereas the ammeter must be connected in series, or in series with part of the circuit. So you must understand how to connect those various apparatus, and we will look at how we represent these in a diagram today so that you know what you are drawing. The purpose of this video is so that you know what these things look like in real life. Then let's go across to the desk and we'll look at so this is a circuit board. You can see the little gold terminals that are pointing up from the board. The board is a wooden board, and then those are just little places that we can connect the various electrical connectors to, so that we have points of connection. Let's look at the desk here. So we have some wire leads that we use merely to conduct the electricity. And we have a globe, so you can see that this is a globe on a piece of conducting nichrome, and we have some that do not have a globe on it. So all those things are just to conduct the electricity, and some of them have a globe on it. And if we look at the globe from the side, you can see how it works. So the globe connects the piece of plastic on the bottom is obviously an insulator and does not conduct electricity. But if we turn it sideways on, you can see that the electricity would travel along here, and then it has to go through the globe in order to keep traveling through the circuit. So that is how these little connections work with the globes in it when they are connected as part of the circuit. Let's connect it all up now and see how it works. Okay, so we want to first of all connect the ammeter in series. So that means that we want all of the electrical current to go through the ammeter. So you can see the black lead is exiting the battery, and the current flows, as we are pointing now, into the ammeter. So all of the current that comes out of the power source will go through the ammeter and then out of the red lead, and it will join our circuit that we have started to create. Now I've just made a very simple circuit with one globe there. Okay, let's just get the other one out of shot because it's not part of the circuit at the moment. And you can see, so the current flows. Once we connect the circuit, the current will flow through all of the leads that we have, and you can see that when I managed to do it, there you can see that we've just got a very simple circuit, and the bulb is acting as our resistor because that is resisting the flow of electrical current and converting the electrical potential energy to light energy. So that is how we are using the energy, is we are converting the electrical energy to light energy. And you can see that as I connect the circuit up and create a path for the electricity to flow, that the globe lights up. Okay, and let's just try and get the ammeter in shot here. Pull it a little bit closer and try and eliminate the glare. So if I, let's just move that. So now as I connect the circuit, you can see that the needle on the ammeter moves. Let's just move the cables out of the way. So as I connect the circuit, you can see, so that disconnected, connected. And you can see that the globe tells you that when let's just make the needle really move. So it's going to move off the scale now, but it's easier to see. So as I connect the circuit up, the globe comes on and the ammeter starts to read that there is current flowing. So we provide a circuit for the electrical current to flow, and current starts to flow. So when current starts to flow, the ammeter begins to read, and obviously the globe turning on tells you that there is electricity. And let's just try and point out now the circuit around which the current is flowing. So if we pick the batteries as our start point, it goes out of the batteries, through the black lead, through the ammeter, into the red lead, through the globe, black lead, and back to the battery. So that is what an electrical circuit is, okay? And while the globe is, and it just continues to go around and around and around that circuit, and because we are dealing with batteries, we are dealing with direct current. So the electricity is always flowing in the same direction all of the time, okay? That differs from the electricity that comes out of your plug, like a plug like that, because the electricity that comes out of the plug is actually alternating current. And alternating current changes direction 50 times a second. So this is direct current coming from a battery, and we are converting so the batteries, our power source, is what is creating the potential for electrical current to flow. Remember that when we think, we like to compare the flow of water down a river to electricity. So by creating a gradient, we create potential for water to flow down a gradient. And so that is what the batteries or the power source does to create electrical potential. That creates the ability or the potential for electrical current to flow. So we call it potential difference. And then we are converting that electrical potential to some other form of energy. In this case, we are using a globe, so we are converting it to heat and light. So the electrical potential energy is being converted to heat and light, and providing resistance to the flow of current, and effectively using up the energy that is being provided by the electricity. And that energy conversion process is what provides resistance to the current flow, and we can speak about that as being work done. So in this case, the globe is doing work and converting the electrical potential energy to heat and light, using that current that is flowing that we can see on the ammeter. Now, if we wanted to actually read the value of current, we just need to change the scale of the current. Now you can see that it is reading, so let's just disconnect and reconnect here. You can see that as I disconnect, the needle drops, and then as I reconnect, the needle goes up, and you can see that we are getting 0.2 of an amp. If I hold it parallel there, we are getting 0.2 of an amp flowing with one globe, and this is obviously a series circuit because there's only a single path to flow in the circuit there. So that is a series circuit. Now let's just change the circuit slightly. So we'll disconnect it and we'll connect up this globe. Screw it down. Remember that we had the ammeter was reading 0.2 of an amp when we had one globe in the circuit. Now what we've done is we've added a globe to the circuit, so we have doubled the amount of resistance. Let's have a look and see what happens to the current. So you can see now, first of all, that globe is on. This I'm talking about this one here that's in the middle of the screen. You can see that it is on, very, very faintly on, and the other one is slightly brighter. But if you look at the ammeter reading, you can see that the ammeter reading has dropped. So as we increase the resistance by adding another globe in series, we decrease the current. Right. So I've just changed the globes around a little bit. Now we have two globes that both work well. So you can see we still have a series circuit, okay? So we've still only got one path for the electrical current to flow. So it comes out of the power source, through the black lead, through the ammeter, which is connected in series, through the red lead, through the first globe, then through the second globe, then into the crocodile clip, through there and back to the battery to create our circuit. So we have both globes working. When we only had one globe, we had a current of 0.1 amp. Okay, oh sorry, it was 0.2 amps when we had one globe. Now we have two globes working, so we have double the resistance. Now you should notice that as I change this, watch the brightness of the globes. See, quite bright and dimmer. So because we are increasing the resistance, when we have two globes, what is happening is you are reducing the current flowing. And what happens over here, so let's just see. So again, now we've got two globes and we have 0.1 of an amp flowing. If I change the circuit and only include one globe, you can see that we have 0.2 of an amp. So we have double the current, and then we can, by increasing the resistance, we can halve it. So the rate of flow of charge, or your current, is inversely proportional to your resistance. So the more resistance you have, the less current that will be flowing. And this is a series circuit, again, because there is only one path that the current can flow. Let's now do something else and build a different kind of circuit. Okay, now what you can see is I've changed the configuration of the circuit slightly. So we've still got the current going into the ammeter and out of the ammeter through the red lead. But then when we get to this point here, I've got the same globe attached there, and the current can flow along there, and now it will flow along with my finger, and it will go to the same black lead that I had. It's now disconnected, but when it connects up to the battery, it will be part of the circuit. But I've added an additional path for the current to flow. So through this black lead, once the current reaches that terminal over there, the current can also flow along this black lead and reach this terminal, and it can go through this globe as well. So we can go through two paths here. So each globe is now on a separate path. So the current that flows through this globe does not have to flow through this globe. And we have two paths that are available for the current to flow. And let's look at what happens when we connect the circuit up. Let's just get the lead on. Oh, we've got a break in the circuit, so there we go. So now you can see there, if I just connect the circuit up, you can see that both globes are on, but we have two paths available for the current to flow. So we have what is called a parallel circuit. Okay, so that is the difference between a series and a parallel circuit. You can see here we have an alternative path for the current to flow. So the current will come out of the battery and go through the black lead, through the ammeter. All the current has to go through the ammeter in series. Will then go through the red lead to the first terminal of the circuit board. Then it can go straight to the globe, which we're touching there, so we're interfering with the circuit. But it can travel along that globe. There we go, all working now. So it can go through that first globe, turn the corner, and get to the black lead. Okay? But not all of the current has to do that. The other current will start at that first terminal, go through the black lead to the terminal that is closest to the camera, and we just have to reconnect that one there now. So you can see that when we disconnect it, you can see that that globe goes off. Reconnect it, that globe turns on again, but goes through the black lead, through the other globe, the new globe, and to the terminal that has the black lead, and then back to the battery. And if we disconnect that black lead, you can see that we are disconnecting. So if we disconnect that black lead, you can see that we now have a series circuit, only one path to flow, all the current going through one globe. Now we reconnect the other branch of the circuit, and we have a parallel circuit with two options for the current to flow. Okay, and now let's just have a look at the reading on the ammeter when we do the same thing. So let's just try and get it in there. Right, let's disconnect the black lead. So we've got, at the moment, we've got, call it 0.4 of an amp, and then when we disconnect it and make it a series circuit with only one globe. So now we have series circuit, only one globe. Just like we had before, we've got 0.2 of an amp, and reconnect the circuit so that we have a parallel circuit. And what we are effectively doing there, you'll have to learn a little bit about this, is that we are actually decreasing the total resistance of the circuit. And because we are decreasing the resistance, what happens is that the current goes up to about 0.35 of an amp. There is what we're getting on the ammeter. So as we decrease the resistance, we increase the current, because that's the relationship between those two variables according to Ohm's law, which you will learn about later. For today, we just want to be sure about what our various elements of the electrical circuit are, and how to draw them. So we've just got one more element to add in, so let's add that one in, and then we will convert this drawing to a diagram so that you know how to draw it. So we've had a look at our ammeter readings and how current flow affects the ammeter. Now we're going to throw something else into the mix here, and we're going to add the voltmeter. Remember that a voltmeter always has to be connected in parallel. Now a voltmeter has very, very high resistance, so it doesn't actually form part of the electrical circuit when you connect it up. It just measures the difference, the potential difference between 2 points. So you can think of that, going back to our water analogy, that's like measuring the difference in height between 2 points on the side of a hill that has a river flowing down it. So you're measuring the difference in altitude, so it will give you an indication of how fast the water is likely to flow down the hillside. Here we are getting an indication of how much potential energy that electrical potential energy that we have as a result of the difference between 2 points. So you can see we've got two leads. So unfortunately I've run out of the black and the red leads, but they have to be connected in parallel, right? So let's go ahead and do that now. So we'll connect it. We've still got our parallel circuit, so we'll connect to the first terminal that forms part of the parallel circuit, and then to the last terminal that forms part of the parallel circuit. And now we will connect the circuit up completely to the battery. So we just need to do that, and you'll see that as we do that, that the needle of the voltmeter will jump up. Okay, now disconnect, and it jumps down, and reconnect, and it jumps up. Again, we need current to be flowing in order for there to be a potential difference. And we've broken the circuit. You can see how sensitive these electrical elements are. Right, so we've just fiddled with the circuit a little bit. Let's just reconnect those terminals for the voltmeter. So that one goes on the last terminal of the parallel part of our circuit. And now we connect to the first part of the parallel circuit. And so just watch the needle on the voltmeter. I'll try and keep it all in shot for you. So you can see so there's still current flowing because the current is still working. But you can see I've disconnected the voltmeter, and now when we reconnect it, it shows you that there is a potential difference we are getting 2 volts in that electrical circuit. Now let's change the characteristics of the circuit. You can see we've got the parallel circuit, so we've got very low resistance. Now if we disconnect this lead here, we'll turn it into a series circuit, and does that affect the voltmeter reading? So you can see that as the current goes up, as the current goes down, the voltmeter reading went up. There we go. Right, so now we've got one globe in a series circuit, okay, because we've disconnected this one here. So we have a series circuit which has relatively high resistance, okay. Then we add the parallel branch and we reduce the resistance, and the potential difference goes, if we can get the circuit to remain stable, the potential difference goes down. Okay, so that's how we can affect the various elements of it. So we can use the various elements of a circuit to affect the current and the potential difference that is flowing around a circuit. Remember that you attach a voltmeter always in parallel, and that a voltmeter has very high resistance and does not actually form part of the circuit. It just measures the potential difference between 2 points on the circuit. So in this case, we are measuring the potential difference between this point and that point, because that's where the terminals of the voltmeter are connected. Then an ammeter, we must connect it in series with the circuit. Now an ammeter has very, very low resistance. We talk about it having negligible resistance, and that measures the amount of current that is flowing through the circuit. Okay, and you can see here, so let's just show you, so this is the voltmeter lead, and you can see that if I disconnect and reconnect the voltmeter lead, that it does not affect the current flowing in the circuit, because there is no current flowing through the leads that lead to the voltmeter. Okay, so that when we talk about an electrical circuit and when we draw an electrical circuit, this is what we are drawing, okay? In this case, our light bulbs here are acting as our resistors. Now, we can draw bulbs. There is a way of drawing bulbs into an electrical circuit, but there are also other kinds of resistors. So we'll go ahead and we'll draw diagrams of this circuit now, and we will show you what symbols to use so that you understand and know what we are talking about from what you've seen in this part of the video. So let's go ahead and draw the circuits that you've seen today now. Right, guys, so here I've just got a simplified diagram of our original circuit that we started with. So when we started with it, I'm just going to slightly change it a little bit, and I'm just going to put the series circuit like that, and then we're going to connect back to the battery like that. So we've got our 3 batteries, okay, and then the lead from the positive terminal of the battery running through the ammeter, which we connected in series, then running to the globe, which looks like that, connected in series, and then back, completing the circuit to the battery. So now let's look at how to draw that in diagrammatic form using standardized diagrams and forms of notation. So your battery, okay, so the positive terminal on your battery is the long line of the battery. So one cell of the battery looks like that, and this side is your positive side, right? And we had 3 cells forming a battery, and that is your negative side. So the long line is the positive terminal of the battery, and the short line is the negative terminal, right? Then we come out of the circuit, and generally we draw circuits as boxes, and we go through our ammeter, which in diagrammatic form we represent with a circle with an A in it, and then a globe, again we represent as a circle with a cross inside it. So that is the notation for a globe, and then we circle back to the battery. Now I'm going to put a switch. We didn't have a switch with the equipment that we had. What I was using as a switch was just to connect and reconnect the circuit. So I'm just going to put a switch in here. So let's just put a switch there, and we represent that with dots. And then an open switch, in other words a switch that's switched off, okay, we draw like that, okay. So that there's no path for current to flow. And then when we close the switch, we need to show that there is still a switch there with those 2 dots, and then we draw a line. So the dots are still there, but that is how we draw a switch, Okay, and we will generally label the switch with an S. Okay, sometimes you'll have more than one switch in a circuit, in which case this one will be switch 1, and then the other switches will be switch 2, 3, 4, etc. And the same with ammeter. We can call that A1. Okay, and then if we have other ammeters, we have A2, A3, and so on. Right? So that is there's our simple series circuit that you saw in the video, and this is how we represent it diagrammatically. Now let's change the circuit, and let's put our other globe in so that we have our parallel circuit, right? So now we have two paths for the current to flow. Let's run that out. Now, how we generally draw that in a diagram is like this. Again, it's kind of neat to keep everything in boxes. And we have two globes in parallel, right? So now we have the two globes in parallel, and what will happen here is so the current has to go through, when it leaves the battery, the current has to go through one wire, through the ammeter, and it's measuring the current in the whole circuit. Comes out of the ammeter. Remember, there's negligible resistance here, so it's just like a piece of wire. And what happens is when the current gets to this point here, which is here, it's got a choice. It can go left or right, right? So let's just use some different colors. And some of the current, now remember with these bulbs, they would have been approximately of equal resistance. So the current would have divided equally either way, but some of the current will go to the left and some of the current will go to the right. And therefore, a parallel circuit is a current divider. So you'll become familiar with that term, and we can represent that on the diagram. We don't put these arrows in, by the way, on diagrams, but I'm just doing it to show you that the current has it can go left or right. There is more than one path for current to flow. So we have a parallel circuit, and a parallel circuit is a current divider because the current divides at that point, and then we'll go along here and come back together again at this point here. So that is how we represent a parallel circuit. Okay, so that's how you draw a parallel circuit. Now let's just bring in some other elements. Okay, so not all resistors are globes. We have other forms of resistors. So if we have something like a heater or an electric motor, we draw a rectangular box. Okay. Like that, so that would be one, let's call it a heater, and if we wanted to put another element in a series circuit, we just join them up. Okay, so that would be now two heaters in series, and depending on what their resistance is, and if we know the values, we can call them, so if we don't know the values, we can call it R1 and R2, and we write inside the boxes. However, if we do know the values of the resistance, okay, then we write those values inside the boxes. Now, resistance has a funny symbol, and it's called the ohm. So it's the Greek omega symbol. So that is 2 ohms worth of resistance that resistor has. Remember that for the ammeter, we talk about amps. So at one stage, we had 3.5 amps worth of current flowing in the circuit. So that is the symbol for current, and your ohms is the symbol for resistance. Here we have two resistive elements in series with each other. Okay? But let's just go back to our parallel circuit and show you how we would draw the voltmeter. So there we have our parallel circuit again, and we connected up our voltmeter. So let's draw the voltmeter in on the diagram. So the way, let's use a different color. So the way we connected the voltmeter up was we connected it up there and to that point there, okay? And we had it connected like that, okay? So to these two terminals here is where we connected our voltmeter. Remember, a voltmeter measures potential difference. But when we draw it on the diagram, we're not going to draw it like that. We draw it close to where it's connected. So we can draw it like that, and we draw a circle with a V, and then again it can have a number, and we can show it connecting like that. Because these 2 points here, that's where the point where the current divided, and this is the point where the current came back together again, so it corresponds to that point there, those 2 points there, and we are measuring the potential difference across those 2 points. Again, the voltmeter measures potential difference, and we represent it with a circle with a V inside it. Voltage is measured in volts, so we could have 6 volts running through that, measured across those 2 terminals. Remember that current does not actually flow through the leads of the voltmeter. It just measures the potential difference between the points where you connect it. So the potential difference between this point and that point is 6 volts. And that is a measure of the amount of work that is being done between those 2 points in the circuit. So work done, you're measuring voltage, potential difference. Those terms all refer to the same thing. And the last thing that we need to add that is crucial to the circuit diagram is we need to add the direction of conventional current flow. Now, before I talk about that, I just want to say that when they made all of these discoveries about electricity, they actually didn't know that the flow of electricity was the flow of electrons, okay? And now we know that electrons have negative charge, and we know that the flow of electricity is the flow of that negative charge. But when they made all of the discoveries to do with electricity, they didn't know that. And they thought that positive charge was flowing. So hence, this is the positive terminal of the battery, and this is the negative terminal of the battery. And they thought that the current flowed out of the positive side of the battery. And hence, when we represented the direction of conventional current flow, we still draw the arrow as if current is flowing out of the positive terminal of the battery. Okay? With subsequent discoveries, as time went on, we now know that it's actually electrons that are flowing, and the electrons actually do flow in the other direction. But because all of the discoveries that have been made to do with electricity before that were based on this assumption, and because it still works to talk about the direction of a conventional current flow being in this direction, we still draw an arrow as if positive charge is flowing out of the positive terminal of the battery, and therefore the arrow is in this direction. So although electrons are flowing this way around the circuit, and we know that now, we still represent the direction of conventional current flow as being in this direction. And when you draw a circuit that has current flowing, okay, our switch is closed here, so we have current flowing, you must have an arrow showing the direction of conventional current flow. And my advice to you is, when you draw your battery and you have your positive terminal of your battery, just draw the arrow immediately. All you need is one arrow. Okay? You only need to show one arrow on your circuit diagram, and that is good enough. It is clear, and that's the direction that you need to show. So that is a little bit of an introductory look at your electrical elements that can form part of a circuit diagram and how to draw them and represent them. So we've had a little bit of a look at them in real life, and we've converted them to diagrammatic form. You should all know how to do that already from what you've done with electricity in grade 8 anyway, but just a little bit of time to revise. Now what we are going to do is we are going to move forward with electricity, current electricity. Remember, we are dealing with direct current here, and we are going to look at all of these various elements that make up the circuit and how they affect the flow of electricity. So here we've spoken about current flow. here we've spoken about the fact that these resistors, or in fact these are globes, but that they offer resistance to the flow of current. So that is resistance. And current and resistance go along with potential difference, which is what we measure on the voltmeter. So we're going to look at those various elements, and we're going to have a look at the laws that govern the values that we can calculate by looking at electrical circuits.